Yeah, you can. Slice.
Oh yeah, I just have to take here. Oh no, it's okay.
There's some lag, is it?
There is a lag. Yeah, I will look there.
Okay.
No, I guess I should look here because you're looking here.
Okay, so I'll try to introduce Rafael. So we are very happy and I'm also relieved that Rafael is visiting us after his welcome yesterday at the Delhi airport. Rafael is an assistant professor at University of Waterloo. He did his PhD at Princeton and spent some postdoc years at University of Toronto. Rafael's interests include algebraic complexity, geometric complexity, optimization, Indian food, and other things. Rafael and I have known each other for many years, most of our academic lives. So I know quite a bit about him, and I offered him the choice of me saying some nice things about him, but he refused to pay me for it. So I'm going to stop and let him talk about British accent.
Thanks for the introduction, Leonardo. Yeah, since he didn't have nice things, I paid him to not say anything. Yeah, okay. So today, I'll talk a little bit about something that I don't know. It's a little bit new to kind of our community, and I learned this at Silence, where he was kind of there as well. And so I just wanted to discuss a little bit more because I feel there's a lot of complexity to write a question there that we should be thinking about. So okay, and so the motivation here that we start thinking about, right, is if you learn about kind of the sum of squares. That's the algorithm that solves everything, and you've heard that whole kind of spiel and preaching about, right? So in the sum of squares, like what is the main algorithm that SOS solves, right? It's just the SDP, like a semidefinite program, right? And how do we represent this semidefinite programs? If you look at the way that kind of the SOS algorithms work, is that they pick an SDP and they represent it in the most naive way possible. They say, no, give me the entire representation, right? The entire description of the SDP. And this is the main reason why these degree lower bounds for SOS are really important to rule out the SOS algorithm approach, right? Because you're saying, well, if the degree is too large, then my representation is really big, and I cannot solve my SDP because just reading my input takes a long time, right? But this is not the end of the story. It just means that this representation is bad. I mean, if we could represent it succinctly, we could go over this degree bound, right? And usually what they also do is they want to prove degree upper bounds to say, oh, I have a small SDP and then my algorithm is already there, right? So, okay. So, and then that's the question, what if these SDPs that we get could have large degree, but not too large, but a small representation? We could still try to get like efficient algorithms, right? So this would allow us to work with these higher degree SDPs, okay? And the question is, how can that happen, right? So how can we work with these things? Well, the thing is, one way is that we can succinctly represent this positive semi-definite matrices appearing in your SDP, right? And if you can do this, then you can at least probe it. You can query a point, right? That you can try to do membership queries and all of that. So, or compute barrier functions if you want to do optimization. Okay, and so today in this talk, like, that's what I'm going to try to entice you is with this question, like it could be more interesting, right? We could have these succinct representations, right? But on the other hand, like, it could also not be, right? That's why they're conjectures. So, all right. So
it's not just a question of representation. And given that representation, you need things which are polynomial time.
Polynomial time computable, exactly. And usually these will come in form of algebraic circles, right?
Okay.
Yeah.
So but in the generality, this cannot be true because if you allow arbitrary degrees, we know how to solve several of these.
Yeah, and it's kind of like linear programming, right? There are some linear programs of exponential size, but somehow like membership queries, we can decide them like through another algorithm, and even though the object, I mean, there's many levels of at which we can do algorithms with things that are prohibitively really large, right? Like we just need other methods of probing it. And this I'm just giving like, you're right, I'm just giving you one next step. It's like, what is the next easiest step? Is if there was another object that I can always probe with that particular object and not with a clever algorithm. Right, you're right, but that's the similar approach. Okay, and so the overview is, right, that since this might not be familiar to many, I think Piyush might be super familiar with this, so I'll bore him a lot. Is I'll talk to you about hyperbolic polynomials and hyperbolistic cones, and then I will talk about semidefinite programming and spectrahedral representations, give a little bit more motivation and tell you about previous work, and then I'll talk a little bit about one result, okay, about kind of lower bounds for these kind of like spectrahedral representation. You just think of it as kind of the most basic STP representation, okay? All right, so let's get started. And if you have questions, just stop me at any time, right? So, all right, so let's just define hyperbolic polynomials. So here, I will just say that boldface X here is going to be a vector of variables, and A is just a point over the reals, okay? And the field here is always going to be different. Okay, and now here's the definition of hyperbolic polynomial. So if you get a homogeneous polynomial H, we say that it is hyperbolic with respect to a particular direction E. Okay, there's this direction E that is special. Is if H, okay, when I evaluate at E is bigger than 0. Okay, and for every vector now that I take in Rn, okay, this univariate polynomial. So if I evaluate in the line passing through minus A here, right? The line passing through minus A and in the direction E. So this polynomial has real zeros. Does that make sense? So in the direction E, if I take any line and restrict the polynomial in that line, this polynomial is real zeros. All its roots are real. Does that make sense? So far so good. So this is what is called a hyperbolic polynomial.
Give example.
Oh yes, very much. So I'll stick with these examples because this is linear programming and this is semi-definite programming pretty much, right? So then so if you take this polynomial, the H of X is just the product of the variables. And E is the all ones vector, let's say. Right? So when I evaluate, I get H of E is equal to 1. And like in any line here, my roots are going to be exactly like the coordinates of A. Right? And when I take kind of M to be like N plus 1 plus 2, and X is a symmetric M by N matrix, and I take the identity, we know that the determinant is hyperbolic, right? Because the determinant of like T times identity minus any symmetric matrix, you know that the spectral theorem gives that this polynomial always had real roots. Right? Okay, so far so good. Okay, so these are kind of canonical hyperbolic polynomials. And what's the hyperbolicity constant that comes from that? Right? So now we have our hyperbolic polynomial, we have our direction, and then we define the hyperbolicity constant as, okay, as the set of points A such that all the roots of this polynomial are non-negative. Okay, so I want not only all the roots to be 0, also all the roots, I want all the roots to be non-negative. They can be 0, they can be positive. Okay? So, okay, so what do we know about this cone? Right? So one thing that makes this cone very interesting to us is that, you know, Gordon in 1959 proved that this cone is a closed convex cone. Okay? And an equivalent definition of this cone, right? Gordon also proposes that proved that an equivalent definition is the closure of the connected component of the polynomial like, of the H. Right? So I take H, I look at the, I can use the board real quick.
Yeah, it's on the yeah, this funky stuff here.
Okay, so how do the zeros of this polynomial usually look like? I'll just draw for like a even degree. It kind of looks like an egg. So there's the center, and then there is this part here, and this is a polynomial degree 4, and my E will be here. Okay, so then if you see, like if I cross any line through E, I have kind of like all the real roots, right? Like 4 real roots. And then kind of the hyperbolicity cone is exactly, and as you see in the reals, right? Like if I look over the reals, if I look at the 0 set, it kind of partitions kind of my space into some connected components. So there's this, the yoke, and then there's kind of the.
What's the picture?
Okay, so the picture is these. So if I draw here the polynomial H, so let's say, right, I have only 2 variables in degree 4, and I'm going to draw the 0 set of my polynomial. So it's going to be like this and this.
Okay.
So these, yeah, sorry, maybe I'll yeah, thanks for the question. So this is the 0 set of my polynomial, right? Whatever I drew. And what I'm saying is that E is here. Okay. And then you can see that this is a hyperbolic polynomial because it has degree 4, and then whatever line I take through E, I exactly have like 4 kind of real roots, right? And then the hyperbolicity cone, what Gordon proved is that the hyperbolicity cone is this set here. That's why I drew it like a convex set, and the outside may not be convex.
So sorry, why is this points through? I mean, these are not lines through E, right? It's lines.
No, I just kind of you should think of E as kind of coming like this, like it's a 3-dimensional picture, and I just kind of flattened it to one affine chart.
Okay. No, but there we are looking at lines in the direction of E, right? We're not looking at line.
Yeah, I'm using some duality here, just to make the picture easier, because otherwise I need more dimensions to do this. Yeah.
Okay.
But this is kind of the picture you should have in mind. But you're right. I'm hiding some of the projectivity in the under the rug here. Okay, so this is how
you only talk about non-negative. You can talk about the function HE minus A by T also.
Okay.
And so
that's this model that comes. Yeah.
Okay. And so you said you always have 4 real roots, and then how did you decide this non-negative cone? Why is that the?
Oh no, this is Gordon's theorem. Right, this is his theorem. Like you can define it like this, but once you define it like this, then he proved that this is exactly the closure of the connected component that contains E.
Okay.
That's the theorem. That's
Okay.
not
Okay, it's not obvious.
It's not an easy theorem. It's not a super hard theorem, it's not a super easy theorem. Yeah. Very good. So okay, so far so good. Okay. And now, like what are the origins of these polynomials? Right? So the origins here, it comes from partial differential equations in some works of Petrovsky and Gordon. And this convex structure that we have here, right, like can be used for optimization, and it was done in 1997 by Osman Guller, and then it had recent applications in combinatorics and optimization. You know, if you know kind of these Gurwitz papers and some Gurwitz and Lee in 2021 that they connect this to like GSP bounds and so on and so forth. Okay, so this has recent applications in DCS, and okay, and now. Like, okay, so let me just tell you, like, okay, once we have hyperbolicity cones, we have the 2 examples, right? That's the product of variables polynomial and the determinant. So what are the hyperbolicity cones for these 2? Well, for that product of variables, the hyperbolicity cone is exactly the positive one, or the non-negative one. And for the determinant, the hyperbolicity cone is exactly the cone of positive semidefinite matrices. Okay, so you can see that this generalizes like very much kind of these very natural objects that we have. So much so that the roots of this polynomial, like HT minus A, they're called eigenvalues of A. Because they generalize the definition of eigenvalues when I have a symmetric matrix. Okay? So, all right. So now, okay, we have convexity, we can try to do like some sort of programming, right? So we have hyperbolicity cones, we're gonna do it hyperbolic program. So, okay, so if I'm given a hyperbolic polynomial with respect to E, and a hyperbolic program will just be the following minimization problem. I'm gonna minimize according to a particular direction, okay, such that X will always belong in the hyperbolicity cone, right? So you can see that this is generalizing already linear programming and semi-definite programming right away, right? Okay. So, and as I said, right, like, so how do I generalize linear programming with semi-definite programming? One way is that if I put my constraints here, my linear constraints, the product of my linear constraints, I'm generalizing linear programming. And if X is here, my determinant of my matrix with AI symmetric, I know that this X needs to make this matrix positive semi-definite. Right? Does that make sense? Okay, so if you have more questions, please like ask.
So here, in some sense, the input to these things is the function h in some implicit form. How should I?
Exactly. You should think of h. I'll give you h in some form, right? Like usually in your programming, I just give you all the linear form, but you could think of give it in any different way, right? Like,
okay.
Yeah. Exactly. So, all right. Right. For example, here, if I just gave you a description of h, and you're able to kind of compute the roots of this polynomial, right? Or approximate the roots and say, okay, with a good enough approximation, you get exactly kind of the epsilon oracle that you usually have for optimization, right? Because usually you also don't have exact oracles. particle. So here you can think of having access to H gives you kind of particle access to approximation of the loops.
Stupid question. What is hyperbolic about? What does adjective hyperbolic mean and all of this?
Oh, it's because like this came from like hyperbolic PTE, so like the nomenclature came from there.
Okay.
Yeah. So, all right. So, and now let's talk a little bit about STPs and spectrahedral set, just so we can get used with this idea, with the word spectrahedral. Okay, so a spectrahedral set, so a convex set said to be spectrahedral if it can be defined by linear matrix inequality. And what is a linear matrix inequality? It's just something that looks like this. So S is, let's say, the set of point C, such that sum of CIAI is greater or equal to sum in the Lerner order, right? So this is just kind of, think about your linear inequalities, just replace the linear with like symmetric matrices, and you want something to be like positive semi-definite, right? So that's what the linear matrix inequality is, right? And the convex set spectrahedral, if there is like matrices A, I, and B, such that S is represented as the set of points that satisfy this inequality, right? And we also say that S has non-empty interior if there exists a point E where this inequality is strict, right? So that should be
just one. You can have an arbitrary.
You can have arbitrarily many, but the cool thing about the spectrahedral is that you can combine them all into one, right? But with direct sum. Yeah. So that's why it's a little simpler. Okay, and actually I put like this footnote here because usually semi-definite program doesn't deal with these like directly the same way that you have the linear programming. The most general form of linear programming, you don't deal only with these inequalities. You can have this kind of extensions, right? Like you can add more variables, you get a more succinct description of your linear program, and you're working actually with projections of these solutions. Right, so usually when you work with linear programming, you work with whatever representation you can get that gives you a small description of your inequalities, right? So, all right, well, I guess Rohit knows, like, for example, if you do like the matching polytope, right, like it has extension complexity very small, so you add a lot of variables and you express with like very few inequalities, right? So then here, STP deals with projections of these sets, which are known as spectrahedral shadows, okay?
Matching polytope doesn't have.
No, sorry, not the matching exactly, like the bipartite, that's what it is. Yes, bipartite. Yeah, my bad. Correct. Okay, so and here's the conjecture, right? That well, Lax did not make this conjecture, he made a more basic version of this conjecture, but then people generalized it, and this is the right way to generalize this conjecture. Okay, and now it's known as general Lax conjecture is if I look at the hyperbolicity cone. Is every hyperbolicity cone a spectrahedral cone? Okay, so that's the conjecture. Okay, and people believe that the answer is yes. And if you think about it, right, we had linear programming, and we know that semi-definite programming can simulate linear programming, but it's a strictly larger set, and also computation is strictly larger, right? And now we have hyperbolic programming, which can simulate semi-definite. And Lax conjecture asks the qualitative generality of hyperbolic programs with semi-definite programs, because if anything that can be a hyperbolic program, right? If the hyperbolicity cones are a spectrahedral set, it means that any hyperbolic program is also a semi-definite program.
But there might be like the representation might be larger.
Exactly, that's the point, and that's going to be the point of this talk, right? Because Lax conjecture doesn't care about this quantitative representation, right? They're saying they just want to know if these are exactly the same sets or if there's something more. For example, right? Like qualitatively, semi-definite programming and linear programming are different because the circle can be represented by, right, a very small algebraic set, but you need infinitely many like linear inequalities, right? So this is that qualitative statement, right? Like, is there more geometrically into one than the other? And people believe that the answer is no.
And a spectrahedral set, not as projection or a.
Correct. Yeah, it's spectrahedral set, not spectrahedral shadow. Yeah, but that's also open.
Okay.
Because spectrahedral shadows, we know that they're more general than spectrahedral sets, because they can have singularities that spectrahedral sets cannot have. So, for example, the ice cream cone like is an example. Like we can discuss it offline, but yeah. So spectrahedral sets are also like a little bit more general, but yeah, but you can also ask the same question, right? And then like it's still open.
So maybe a basic question. Do we know of hyperbolic polynomials that look very different compared to the determinant and product of linear polynomials? I mean, I'm just hoping that so that it doesn't directly seem like either it's an LP or an STP.
Right, so the elementary symmetric polynomial is a polynomial that is also hyperbolic. Yeah. So,
but we know that the cone is that.
We know that the cone of that is spectral.
Oh, okay.
It's a beautiful paper by Bernadette, and
With respect to what point? The all ones point?
all ones point. Yeah.
I see.
It's similar to the x1 to xn, but
Any
that is an elementary symmetric point. You're saying all elementary symmetric.
All of them are, yeah, exactly.
Are there operations within which you can produce more hyperbolic polynomials from another?
Right, that's a great question as well. Like we know, we don't know many operations. If you multiply two hyperbolic polynomials, like that they're hyperbolic in the same direction, of course you get but the cone is kind of the intersection of their cones, and there's some other kind of symmetrization and things like that. But it's unclear, kind of constructivity of those hyperbolic polynomials. Whether it's an interesting question as well. Like how can we produce more? Okay. All right. More questions?
But it is, if you take any homogeneous real stable polynomial, then it is hyperbolic in the one direction.
So okay, real stable, right? Real stable means hyperbolic. So real stable polynomial means already that you're hyperbolic, and your hyperbolicity contains the non-negative word. That's what it means. Yeah, when the homogeneous set.
Yeah.
Right. So all right. Right, and that's again in kind of picture, right? That's what the generalized conjecture is saying. But we know that the first one is proper as we discussed, and Lax conjecture is saying that the second one should be inequality, qualitatively speaking, right? Okay, so and the original conjecture was only for hyperbolic polynomials in 3 variables, okay? Because Lax are just interested in those 3 variables, and there hyperbolicity cones and kind of hyperbolic polynomials are kind of in one-to-one kind of correspondence. So then he just asked this question about the polynomials, and that's why the generalization had this didn't have the convex set. And it was proved by Helton and Vinikov in 2007, okay, using very fancy techniques, and which I won't discuss here. And and then now we have the general conjecture, right? So
how many variables did they have to go to in order to?
No, 3. That's it.
So anything are also in.
Yeah, because you have to prove if they're spectrahedral sets, not shadows. They just prove spectrahedral sets. So the same number of variables. You can't get around that. Okay, so then as we kind of discussed already, right? We're computational people, so the generalized conjecture is about this qualitative aspect of FDPs. Now, can we get quantitative aspect between them? Right? Because that's what we're interested in. And also, another question that's very interesting is that, okay, maybe are there sets that we can represent with kind of hyperbolic programs that somehow the algorithm there can do better, right? Right now, the only way I can see it is that the object does not have a representation by small FTPs, but it has one with small hyperbolic polynomials. And then there you can get a better algorithm, right? Okay.
And then even, variables don't change, but the number of the spectrahedral thing, you have to give a bunch of matrices of specification. Is that one number of matrices you need to give for even the 3 variable case? Is there a bound on them or?
Oh, sorry. Yeah. So the question, yeah. So let me say the original Lax conjecture, right? Because I think, yeah, okay. The original Lax conjecture was just about is every hyperbolic polynomial a determinant of some symmetric matrices? So that was the original question. It's a bit more precise than just the cones. And sorry. And that's what they proved. Yeah. Yeah, my bad. Sorry.
So it's 3 cross 3 matrices.
No, not 3 cross 3. It's any T. Yeah, exactly. So it's just 3 variables. Yeah. Okay, more questions? Okay. So then the open question here is this quantitative generalized conjecture. So is there a hyperbolicity cone which is simple? And by simple here, you should think a small algebraic circuit. Right, it can be computed by a small algebraic circuit, but any spectrahedral representation of it requires matrices of large dimension. Right, so that would be a nice thing to have, because this would show that kind of hyperbolic equivalence give you a much more efficient representation, right?
So when you say small algebraic, that you're giving the polynomial and defining the cone.
Exactly. Suppose the hyperbolic polynomial has a small surface.
Do you care about the degree being small in the number of variables or any such thing?
Yeah, we do care about the degree being small because, so, okay, I don't know if I will say it or if but it turns out that like, when you look at, so the degree of the hyperbolic polynomial, right, is related to like the self-concordant barrier. So if you want to like, if you want to use interior point methods, which is usually what you have when you use H, right? Like, so if you know a little bit about interior point methods, you know that like you have this determinant, right? Like, and the determinant, like you take minus log that for this barrier, right? Like, and this minus log that when you're doing interior point methods, you can do exactly the same. For hyperbolic polynomials, you just put minus log of H. So it's important, and the degree of your hyperbolic polynomial is related with the self-concordance of this function, which gives your play. So if your degree is really large, then that's bad, right? All right. So more questions?
Wait, the first open question, is that the quantitative generalized conjecture, or that provides a counterexample to the quantitative?
Yeah, no, I mean, so okay, I said like quantitative general conjecture, but I don't want to be so bold I will be bolder later, right? I don't want to be so bold now. I want to introduce nicely and then get bolder as things go. Yeah. So yeah, I don't know what to conjecture, to be honest, right? Yeah.
So, I mean, do we even know how to prove any kind of lower bounds on the representation, spectrahedral representation of complexity?
Very good. I'm going to get to that in a couple of slides.
So not just about the hyperbolicity code, but any kind of lower bounds do we have?
Right. So I'll get to that. Well, I will get to what we know. Like when I will do the lead review real quick. Yeah. So I'll answer that in a little bit. And okay. And then this open question here is also like, just can you give me like a hard hyperbolicity cone just to begin with, right? So like, is there an explicit hyperbolicity cone for which any spectrahedral representation requires matrix of large dimension, right? So I don't need, the comparison here is that here I'm saying that the hyperbolicity cone is simple, but here I just want any explicit hyperbolicity cone, right? So, all right. So, all right, answering to archetype now, like, what do we know about like lower bounds, right? So, okay, there are non-explicit lower bounds on the size of hyperbolicity like cones, okay, and this is proved by Ryder, Raghavendra, Prasad, Nikhil, and Vine in 2019, okay, and what did they prove? They proved like exponential lower bounds on the dimension of the minimal spectrahedral representation of some non-explicit hyperbolicity cones. And what are those? Like, those are known to be spectrahedral because they come from elementary symmetric polynomials. Okay, so you perturb the coefficients of elementary symmetric polynomials in a way that it's still spectrahedral, like the cone is still like spectrahedral, and then they're able to, but you perturb by many small perturbations. Right? So you get a large family, and what they're able to prove is that one of them will be hard. Okay, so then that's in the sense that it's non-explicit, right? So because this lower bounds for some polynomial and a large set of polynomials, and these are again perturbations of the elementary symmetric polynomial. Okay, so they use this non-explicitness to be able to prove lower bounds, and the proof is a little bit involved.
Is it some kind of counting argument?
Yeah, there's some dimension there and some quantitative dimension that they have there that they're able to give this lower bound. And they also have like a Hausdorff dimension, like in terms of convexity, that they construct this family of cones that have some geometric property, because they're also interested in like approximating the complexity of these cones, right? Because it's the same way for us, right? We're also interested. I mean, the bigger question, I mean, I'm just asking the first question, like the easiest questions, and then you can say, okay, but in optimization, we're interested in a little distortions of these, right? And in terms of explicit lower bounds, right? So a little, I guess these are the two like grounds. Like the only lower bound that we know is by Mario Kummer in 2016, which it gives optimal lower bounds on the dimension of the minimal spectrahedral representation of the Lorentz cone. Okay, so this is a hyperbolic polynomial in the direction like 1, 0, 0, 0. Okay, and so this is a spectrahedral cone. Okay, it's pretty much like the cone that you can imagine, right? And then he gives linear lower bounds on the linear here in terms of n. So he proves that any spectrahedral representation for this cone has to have size like n over 2. Okay, and these are optimal lower bounds because we have like upper bounds for this. Okay, and this is the only like lower bound that we know for spectrahedral representation.
So the conjecture earlier said, let's forget about the size law, the quantitative aspects of it. Can the
Right, can this Lorentz cone here, right, which is a hyperbolicity,
can this ever be even be represented by
spectrahedral? Exactly, and that we already knew for a while, right? Like this Lorentz cone is known for a while, right? And we knew actually a representation with matrices of size n over 2. And then Mario in 2016 gave a lower bound of n over 2.
so it's possible that the answer to that is no, meaning
It is very possible that the answer is no.
but the lower bounds here are sort of so in that case this lower bound will not be once we have a proof of that, this one is super interesting.
Exactly. Right, because what we want is something that's computationally prohibitive, right? We want some exponential gap, and this is proving like a All right, so good. Any questions so far?
So there are also these SDP extension lower bounds. So how are these two questions related? Or
Correct. No, and that's very good. And I'll ask more questions about this later as well. So when you talk about like SDP extension, what you're looking at is exactly spectrahedral shadows. So then, for example, when Prahlad asks, oh, what about the question of like hyperbolicity going to be represented as spectrahedral shadows? There's a lot of work being done there as well. And we know that kind of smooth hyperbolicity cones are spectrahedral shadows. So this kind of corroborates more and is a proof that is not like the proof uses the Laster hierarchy and we don't know any computational bound there. Like we just know that one exists because of convergence of the Laster series. It's not a and use some G theorems too. It's quite impressive by Netzer and semialgebraic.
So we know some exponential SDP extension.
No, we know some. No, there's no. We just know that there exists a represent. We don't know bounds of this representation. It's some convergence that we don't have a bound for. We just know that it will converge when your hyperbolicity limits is smooth. When your hyperbolic limits is smooth.
No, I meant in the lower bounds thing. Are there some exponential lower bounds known for SDP extensions?
For SDP extension. So the lower bounds that are known there are for like the So isn't that the lower bound for like the matching polytope and the
the NP-hard problems?
They're NP-hard, and then the thing there is a little bit of cheating, right? Because you're saying I'm picking a polytope that has like exponentially many kind of inequalities and yada yada, and then they give a spectrahedral bound, but then you're already cheating because it's like you start with an object with really high complexity, right? And then you say, oh, this object that's hard is really hard.
Okay. That's
what they show, right? And in this language, I mean, not to dismiss their work. I mean, their work is amazing, right? But
so you're saying
in this setting here, it just feels a little bit trivial because you're saying I'm picking like a hyperbolic polynomial of exponential degree, right? Which is this correlation polytope. I mean, it's like has exponentially many inequalities, and then like when you represent it with a hyperbolic polynomial, you can't represent it small either. And saying, oh, look at this hard object already, it has exponential degree, and I'm going to give you a lower bound like. Or spectrahedral shadows as well, right? I mean, it's amazing work, but in this line here, it kind of feels like cheating the. So, right. So, great question. I don't know if I'll talk about it. I think. Okay. And we don't have again super polynomial lower bounds, right? And that's kind of where we go from here. But even these questions are quite interesting, right? So, more questions. No, keep going. Good.
So when you say explicit polynomials. So you are not considering these exponential degree.
No, I wanted an explicit. I think I should have said. Okay, thanks. I will update this. Right, I should have said explicit polynomials of low degree.
Oh.
You're right. Because in that sense, that is explicit, right? All right. So and now let me just say a little bit like some things that we did. So we just gave a conditional lower bound for spectrahedral representations, and I'll talk a little bit about, you say, okay, but there's these polynomials and the polytopes, how do they relate, right? Like, how can we hope to show any computational like complexity bounds. And I'll just show like some equivalent formulation that's much more amenable to like algebraic techniques. Okay. All right. So what is the result here? So okay, I'll use a polynomial that's very dear to Pilush, right? Which is the magic polynomial. You can ask him all about things. Okay, so he knows much more than me about it. So what is this polynomial, right? So I'll just give the homogeneous version, like to make it hyperbolic as Amini did, but this polynomial is very studied, like since Lieb, I guess, studied it first, right? Like back then in the days, right? How Lieb. Yeah. So all right. So okay, given a graph, okay, let's take an undirected graph. And for each vertex, I'll give you a variable like xv, and for each edge, I have a variable we. Okay. And okay, now let's say that mg is the set of all matches of g. Okay, g is not bipartite, it's just any graph. And I'm just taking all matches. Okay. So these matches don't need to be perfect, right? Like they're all just the matches. Okay. And then for any matching in this family, let's say that Vm are the vertices that are here in this match. Right? So then the polynomial mu of g in these variables x and w, okay, is defined as this weighted sum. So I have this sum like -1 to the power of the size of the matching. Right, so this is the number of edges. And then I multiply all of the vertices which are not vertices of the matching. And then I also multiply by all of the edges that participate in the matching square. Okay? So Amini showed that this polynomial is hyperbolic, and the hyperbolicity cone of this is spectrahedral. Okay, this took a lot of work. I mean, this is kind of one of the main results of this paper, right?
With respect to what direction?
Well, yeah, with respect to the direction, like ones in x and zeros in w's. So the x is all ones and then w is all zero. Okay. So and in this, like I proved in 2020 that a lower bound for the complexity of the hyperbolicity cone of this polynomial. Okay, so what we proved is that if you just take G to be the complete bipartite graph, okay, then the minimum spectrahedral representation of the hyperbolicity cone of this Mg will also be super polynomial, assuming that Vp is not equal to N. Okay, so it's a conditional lower bound. Okay. So is the statement clear? So if you believe Rinal and Ramprasad that Vp is not equal to Vnp, then okay, this matching polynomial, like the hyperbolicity cone is hard for the complete bipartite graph. Okay.
But you expect that result to be true even if I don't believe them, no?
Oh yeah, I very much expect. Yeah. You can not believe them, and I also believe that this should be hard. You can believe huge, right? Like, huge might be more believable. Because he studies the roots of this question, right? So he addresses the roots of this polynomial. All right.
So the cone corresponding to this complete graph,
Yeah.
is there a simple description for this cone?
No.
No.
Yeah. So, but there is something interesting about this, right? Because the constant coefficient of this polynomial, the constant in x, is the permanent. That's where the hardness comes from. As this has a hard coefficient, and that's what we exploit. And that's the funny thing that this proof does not have much to do with the geometry of that column. Because I'll pick one coefficient and it's enough for me.
The constant in x.
The constant in x.
The pure polynomial in
If
W.
this is the polynomial in x and w, right? So if I just
Matching.
I get all the perfect values. Exactly. Yeah. And those are all the perfect values of the complete bipartite graph. Right. All right. Questions? Okay. So then, all right. So before I talk about like how this proof of this theorem will go, right? Like let's just talk about kind of how do we get to this, right? To this generalized conjecture. What does it have to do with algebraic complexity? So there's an equivalent formulation to this question, right? So, and here's the thing. So if H is hyperbolic, right? So we want to ask, does there exist a dimension G and a symmetric G by G matrix is such that the hyperbolicity cone is a spectrahedral, right? The right side is a spectrahedral representation, and the left side is our cone, right? That's the question that we're interested in. So here's, before we make it more algebraic, like remember, oh, the hyperbolicity cone for the determinant is the set of all positive semi-definite matrices, right? So then let's look at these polynomials that are defining these spectrahedral sets, right? So, and then we get to this definite determinant representation. So we say that a homogeneous polynomial H has a definite determinant representation at this point E, if there are symmetric matrices A1 up to AM such that this weighted sum of EI, AI, is positive definite, right? And H can be written as the determinant of this polynomial. So this is a definite determinant representation for the polynomial. Does that make sense? So clearly, if I have a definite determinant representation, I'm a determinant in the form hyperbolic in this direction, right? But now, not all hyperbolic polynomials have this. The last conjecture was that in 3 variables, they all have this representation, right? But now when you go to more dimensions, it's no longer true by a dimension counting argument, right? So you know that there's a lot more hyperbolic polynomials, okay? So now, and here's the equivalent formulation, right? So for each hyperbolic polynomial at E, there exists another polynomial Q, which is also hyperbolic at E. And then we also know, like, this is the conjecture, right? So if you believe that the Lax conjecture is true, you believe this. That for any hyperbolic polynomial at E, there is another hyperbolic polynomial Q at E, such that the hyperbolicity cone of Q contains the hyperbolicity cone of H. And why is that? It's because when you multiply them, the hyperbolicity cone you get is still the hyperbolicity cone of H. So you're preserving the hyperbolicity cone. And H times Q has a definite determinant representation. Okay? So this is an equivalent description of the last conjecture. Okay? It takes a little bit of real algebraic geometry to prove it, but it's not like super hard. Okay? I can do this offline if you like. Okay? So, okay, so now you can see that there's a little bit of algebraic complexity, right? Because the determinant, yeah.
So the proposition is that this statement is equivalent to the Lax
Is
conjecture.
equivalent to like that's the proposition. Correct.
Ah.
Yeah. Right. And right. And now clearly this is very kind of related to algebraic complexity because the determinant is the only polynomial that exists, right? Like if your polynomial is the determinant, that's what we know, right? And this is exactly a question about, oh, I can multiply by something and get a determinant, right? So now we're in business, right? Because now clearly here we have like an algebraic version of the geometric question.
No. This is the first time you're stating the generalized conjecture formally, or you stated it?
No, the formula is every hyperbolicity cone spectrahedral. Right?
That's what you call the generalized conjecture.
That is the generalized conjecture. Yeah. And this is an equivalent formulation of it. It's a proposition that is equivalent. Okay. Right.
So if you additionally believe that the answer to the generalized conjecture, or rather, if suppose the answer to the generalized conjecture for a specific polynomial was yes, but that you expect a lower bound in the spectrahedral representation, that would somehow translate here as the degree of Q being very large or something, or is there some?
Yeah, exactly.
Okay.
Yeah, exactly. So so what Rafael is saying, which is exactly like very good. It's good that you guys can do my talk, right? It goes by itself. It's good. So yeah, the question on the lower bound here is exactly like, oh, if I multiply H by Q, the Q that I need has large degree because then the determinant becomes really large, right? Because the determinant of size D, we should just say like this determinant of complexity G. So if we want a lower bound, we want to say that this has to have really high degree. That's correct. Okay. So far so good. So everyone kind of understands well, without the proof, but believes this is also equivalent. Okay, so now we're in business.
So Rafael, one question about this definition.
Yeah.
So if you there are two conditions.
Yeah.
So if you remove the first one, then every polynomial has this kind of representation.
No. Yeah. So those are not okay. So every polynomial, right? Every polynomial can be written as a determinant of some symmetric matrices. That is correct, right? It was proven by Kaltop and René and Portier, right? 2012 or something. So you're right.
No, but this,
But this
this would imply that it's scale stable.
no. But the whole point, yeah. So the whole point, no, it's not necessarily. So it can be like written by any letter. Yeah, exactly. They're not gonna be PST, right? So yeah. That's the difference there.
Only one direction.
Exactly. Yeah. So the whole point is ensuring these positivity relations to hold, right? Which is again another way that if Prahlad's saying like, okay, if I don't believe in Linal and Ramprasad, right? Like this has some monotonicity kind of built in. And that's where like this is much more believable than kind of like this does not need to have much complexity like this general like statements, right? We should be able to do more, but somehow ensuring this positivity is really hard. And for example, like I tried like elementary symmetric polynomials, like 5 variables, like degree 3 or 6 variables degree 3, like where things get like murky. And you're right, you can get a symmetric like description of this, but then it doesn't satisfy the positive definite. And it's really, and to get one that satisfies you just blow up the size by a lot. So like I've been tinkering with this for a while. All right, so far so good.
And so it just needs to be this positive in some direction E.
Correct. In the direction in the cone. Yeah.
So that okay, that looks like a simple condition.
Yeah. And say that to Burbis. I said that he almost got a black eye. Right. So and that's my like heuristics to be hard. And the Leonid told me it's hard. So I very much believe Leonid's intuition. All right, so okay, so now let's see how to prove this theorem, right? With some kind of known things. Since we're in India, so all of you know all these things. I'll go quickly through this. Okay. So what is there's a theorem by Kalthofen, like a seminal theorem by Kalthofen, that if your polynomial, okay, let's say in being dp just means that it's an easy polynomial. It's an easy polynomial to compute. If you can compute f efficiently, then you can compute all of its factors efficiently. And by computing efficiently, it just really means that, okay, there's a small determinant that computes it. That's all that we need to know about this. And then, okay, so what is the corollary of Kalthofen's theorem, right? Is that if f is hard, then all of its factors are going to be hard. Right? Or, sorry, if f is hard, then all of its multiples are going to be hard, right? Like, I'm sorry, right? So that's the contrapositive, right? So if you have a hard polynomial, the hardness translates to all the multiples. And now we start getting, okay, like I know this result, and I know that this spectrahedral complexity has this multiplication, like being hard, right? So maybe this should be useful. And that's exactly how it goes, right? So if you just combine Kalthofen with a little bit of real algebraic geometry, it yields the lower bound, right? Because the bit that you need is exactly to get, you use the real algebraic geometry to get this equivalent formulation. And once you have this equivalent formulation, you need a little bit more of algebraic geometry just to show that this matching polynomial is the minimum polynomial describing its hyperbolicity cone. Okay, so you need a little bit of just to say like, okay, there's no factor of this matching polynomial which is describing that convex cone. So once you use a little bit of algebraic geometry to prove that, and you know now that the matching polynomial is the simplest polynomial that you can get, now you know, okay, now all we need to do is to prove that the matching polynomial is hard, right? But then, well, okay, the matching polynomial being irreducible is what you need to use for the real algebraic geometry to say, okay, if I'm irreducible and I represent a cone, I have this representation, then I know that this is the minimum representation. So any other polynomial represented in this cone has to be a multiple of the matching polynomial. Okay, and then, okay. That's what we were saying, right? Irreducible polynomial minimally defines the variety, and then we get the multiple. Now we're very close, and then the only thing we need is like to show that this matching polynomial is hard. But how do we know it's hard? Well, we know that its constant coefficient, which is not any coefficient, right? But its constant coefficient is really hard. And when the constant coefficient is hard, then your polynomial better be hard.
So you set size to 0.
Yeah, you just set x to 0 and you get the permanent, right? So any circuit that computed, you get a permanent of squares, but it's really easy to reduce to a permanent. So then, like once you know that your constant coefficient is 0, then you know your polynomial must be hard, right?
So the irreducibility, does it come from just the fact that the roots are distinct or that?
No.
About the univariate cases. So
Yeah, so that exactly. So I don't use I cannot use the univariate case, right? I have to use the many variables to prove irreducibility. Because I know,
but if the univariate one is irreducible than the multivariate one.
The univariate one is never irreducible, right? Because it will have degree more than 2, right? So it's never irreducible.
yeah, it always like if you specialize.
This is oh, sorry. So
Univariate,
The univariates are of degree 2, right?
Yeah.
but over R, degree.
Only degree 2.
no, I was completely. I was thinking of squared factors. So that it doesn't have it's square thing.
Yeah, it's perfect. Yeah.
But that doesn't mean.
Right, exactly. You can have many, exactly. Right. And
So again, what kind of what's the quantitative relation? So if you say that permanent requires quasi-polysaccharides or whatever.
it's exactly that relation, right? Because
that.
yeah. Well, it's whatever the determinantal, like, okay, you assume VP not equal to NP in the determinantal setting, right? I separate like the determinantal complexity of the permanent.
But do you, because you have to work with the determinantal representation, do you lose a log-n factor in the exponent in the whole thing, or you don't? If you're going to use Cartesian.
Right. No, but Kaplan is just saying VP, right? And then like VP is even stronger than the determinant.
But this factoring closure, you need only for circuits, or do you need it for the dead?
Well, I just use circuits, and then I say, well, any determinant computing the circuit, right? Like that it only works in my paper.
Oh, it goes the other way.
Yeah, it goes the other way. Yeah. Very good. Okay, so that's the thing, right? So once we prove that, and we already know the magic polynomial is hard, then that's it. Like any multiple of the magic polynomial will be hard, right? So far, so good. So this is what gives us the theorem. Okay, so it's quite simple. That's it. And now, I'll just, if you can, do you have questions about this thing, I can conclude, and we can talk more offline if you want as well. I'm around. So okay, questions. Okay, so what do we do, right? So we just proved like kind of the first super polynomial lower bound on the side of any spectrahedral representation for a very specific polynomial of low degree, right? Which is the magic polynomial. But again, you need to assume VP not equal to VP, and I very much feel that this should be removed. Okay. Okay, so what is the problem with it? The lower bound is conditional, so clearly an open question there is to remove that. And also that's the thing that we were talking about, that the explicit polynomial that we give is also hard to compute, right? So much more like if you want to do optimization, you would like a polynomial that's easy to compute, to be able to separate hyperbolic programming from semidefinite programming. So we have to take steps in that direction, right? So okay. And again, right? Like so we have this open question that we would like a simple and low degree kind of hyperbolicity polynomial, hyperbolicity cone, right? With like really large spectrahedral representations. And then the other question here is explicit hyperbolicity cones, just any explicit hyperbolicity cones with super polynomial dimension. Right, but again, it needs to be with low degree, right? So now that I kind of raised these questions, I just wanted to say that these are just the beginning kind of the rabbit hole, right? There's a lot more questions that people would be interested in, and the optimization people would care about, right? So, for example, this is also a quantitative approximate generalized conjecture. So, usually we're interested in approximations of the hyperbolicity cone. So, just proving a lower bound for this hyperbolicity cone does not rule out that there is another just perturbation of it that's very close to your cone that's very easy to compute, right? And this is what the optimization people really care about, right? Because any approximation cone, you're like, okay, the world is not like perfect, so I can work with any approximation, right? And that would be good. And we know this for like non-explicit, right? We know that among a collection of hyperbolicity cones, like there's one of them that's even hard to approximate. That's the work of Srivastava and Raghavendra and Ryder and mine. Okay. And okay, so this is the open question. Clearly that's still open. And again, even for spectrahedral shadows, it's open. And this is the other question as well, but now we can say the same way that Prahlad asked about spectrahedral shadows, we can also ask about computational variants of the spectrahedral shadow. Okay, so you can say, is there an extended hyperbolicity cone for which any spectrahedral shadow? Now I have allowed projections, but I want to say the spectrahedral shadow representation of this spectrahedral cone, okay, requires super polynomial dimension. Okay, so that's one. And this last question is even open for non-explicit polynomials. Okay, so the work that I mentioned does not work for spectrahedral shadows. Okay, and there's many more questions there. I mean, you can just pull out everything that the optimization people want, and you make an algebraic question out of it, right? So there's many more of these. So yeah, it's both conjecture time. I mean, I didn't show the question, but I
No, I was going to ask, for example, the first question, if you assume that the permanent is not even in VP bar,
right.
so do you get something close to the first question? I mean,
Yeah, so that is also not known, right? Because the notion of approximation there is not the same notion that you have for bar. So those don't translate necessarily to one because the approximation dimension, like at least the one that I talked with Nikhil about, is this Hausdorff dimension of the cone, and then you kind of look at the cone in a particular ball, and then you look at the Hausdorff distance there. So I'm not sure how that compares to the algebraic definition. But that's an interesting question. Yeah.
now I'm very curious
Can
about
I
the next
reach?
few slides.
So all the hyperbolic programming which is there. So is there a natural combinatorial problem for which there is a very clean hyperbolic programming formulation? It might have also a spectral LDP formulation, but which is not as clean. So I would like to see something for which hyperbolic is really powerful over.
Yeah.
So what
The elementary symmetric polynomials, for example, right? Like the hyperbolicity representation is right there. You can just compute. You have the elementary symmetric polynomial, and you try to write this as an STP, it just becomes a monster. Like so. So I believe that this is where we should experience the separation already. But I just don't know how to prove it. But you're right. That's my only example that I've.
So we don't have
appreciated.
small STP representation for.
No, but we know small spectrahedral shadow representations. It's a work by Parillo and Sanderson, and I don't know how they look from their work. The representation they give is through construction of a sequence of maps, and these maps give you a spectrahedral shadow projection. But I try to unravel those definitions, and I still can't.
But moreover, it's a shadow, it's not.
It's a shadow, yeah. It's a small shadow, but I don't know any small spectrahedral representation, just pure spectrahedral representation.
That's okay. And when does it become at the highest degree? It's in linear programming for EN, like the product of xi was just linear programming.
Exactly.
So does it become hard already at n-1, or so when you look at the elementary symmetric polynomial?
No. It has to be kind of deep down. Yeah. Exactly. Yeah. So okay, questions here?
Okay. So the top is linear programming.
Right.
Where the LDP come in this one at all, or
No, STP does not come in this sequence, right? It's just a series of different cones.
okay.
Yeah. Yeah. Okay, so far so good. All right, so then now it's time to unleash the bold conjecture time. I follow the people I admire, so now I'm going to pose some bold conjecture. So, all right. So here are some targeted conjectures, because you might think, okay, so how should we think about it, right? Like what questions can we pose just to say they're right or wrong, right? So it doesn't matter. I'll just pose them as correct and challenge you all and say that it involves a lot of hard tools to solve, and maybe you solve it and show me that I'm wrong. So targeted conjectures here. So let's say that SF is the size of the algebraic circuit size for polynomial F, right? The minimum size of an algebraic circuit computing F. And then LF is like the formula size. Okay, and then S home of F is just the minimum homogeneous circuit size for F. Okay, all right. So, and I also have the monotone size. So I have my polynomial here. If I have like non-negative coefficients, and I forgot to say later, but like you can just, if you're real stable, okay, you can assume that this is without loss of generality. Okay, so let's just work with real stable because they're pretty much all the hyperbolic polynomials they're kind of twins. Okay, it's just a normalization. So that we can assume that all the hyperbolic polynomials satisfy this. Okay, and let's define the S1 as the minimum size of a monotone circuit, right? And here are some conjectures, right? So Okay, and I'll define just the spectrahedral complexity based on the polynomial, right? So as lambda will be the spectrahedral complexity, and this is like phi for projection, right? So this is the complexity of the spectrahedral shadow. Just so that I can give this kind of, to say the conjecture very succinctly.
And where does E come in?
Oh, I just say it's always with respect to E. So like let's say that E is the all-one vector, for example, okay? We can always kind of assume that because we can just change the polynomial. So okay, so here are some conjectures. I think that the complexity of this, the spectrahedral complexity of the hyperbolicity cone, assuming the spectrahedral, right? Then this is polynomial in either the homogeneous complexity or on the monotone complexity. Okay. So, okay, and so clear, like this is much larger, right? So I believe that this should be the thing that dominates, like the monotone complexity. Because spectrahedral has this monotonicity to it, like has this monotonicity field to it, right? So then I'm just kind of conjecturing that like the spectrahedral conjecture will be polynomially related to that.
So the homogeneous complexity will always be okay if you are willing to tolerate. Oh, maybe that's the point, that you are not willing to tolerate poly D factors. Yeah.
Well, the conjecture as you stated here is not what you.
No, it's not exactly.
Not what you said. You said it's polynomial in this or polynomial in that. That's not what's written there. Or is that the same
I
thing?
mean, which polynomial and whichever is larger.
Yeah, whichever is larger. Yeah. That's why, like.
So the elementary symmetric polynomials homogeneous complexity is large, is it? Because the monotone complexity is small, right?
Right.
So the homogeneous.
No, the monotone complexity of the elementary is high. That's debated by Yehudayev and Rubish. Rubish and Yehudayev, they have they have a homogeneous complex, like homogeneous in terms of the circuit, not like the circuit computing homogeneous polynomial. I don't want cancellation. I want that homogeneous complex. Every gate computes homogeneous polynomial. So this homogeneous complexity is large for the elementary symmetric polynomial, like by Rubish and Yehudayev. Yeah. So if you prove that this is related, then you get a lower bound, right?
I'm getting a little confused. So we can always make any circuit homogeneous, right? So with the D squared blow up. So what am I missing here?
Like, oh no, right, like the general case, right?
Yeah.
No, like I'm not sure. Like, okay, we'll talk this offline. Let's just remove this one. Let's just say homogeneous and S is the same.
Okay.
But I want to say that like the monotone complexity is what I'm more concerned about.
So monotone also, so the matching polynomial, the multivariate version is real stable, but it's not mono. Has negative signs.
Yeah. Oh yeah, sure. Like I can stop here. Yeah. Okay. We'll do that. Okay. So let me just say here, like the monotone and the complexity here, and I say that the projection here has to do more with the circuit size or the formula size, and here I think it's the monotone that we've covered it. So let me just leave the conjecture. The actual one, I believe this should be related to the monotone complexity, and the other one is just the full circuit complexity. And that's why, for example, elementary symmetric polynomial has a small spectrahedral shadow, but maybe it does not have any like small spectrahedral representations. That would be my line of attack to this. Okay, and then let me finish. And okay, yeah, that's actually it.
Okay, thanks for the wonderful talk. Are there other questions? Yeah, now we can continue forever.
Maybe you go out line first.
Yeah.
We need to have a safe space. Oh, this is to be recorded.
There was a paper by Affiliation, right? Or shadows of